Hello friends, welcome back to Scientific Blunders, where you learn the don'ts first. So we're going to continue our series on limits today, and I thought we'd discuss one of the most powerful and beautiful rules in limits, known as L'Hopital's rule. And I apologize to the French folks if I'm terribly mispronouncing this name, but L'Hopital's rule is really powerful. And for those who are not familiar with the rule, let me give you a quick example. So L'Hopital's rule says if you ever encounter a limit of the form 0 by 0 or infinity by infinity, then all you have to do is simply take the derivative of the numerator and the denominator and apply the limit again. So maybe that sounds a little complicated, but one example will really help you understand how to apply the rule at least. So in this video, we're not going to really look at the proof of the rule. We are not going to try to understand why the rule works, but let's look at a few examples. Okay, so the first and classic example of L'Hopital's rule is the limit of x tending to 0 of sine x over x, right? And so with any limit problem, the first thing you want to do is just try and plug in the number into the function. So sine 0 over 0 is 0 over 0, which is of the form that L'Hopital's rule requires the function to be, right? So what L'Hopital's rule says is, okay, now it's 0 by 0, so that's indeterminate. So what you do is take the derivative of the numerator, okay? So you apply the limit again, but this time you apply it to the derivative of the numerator, which is cos x, and divide that by the derivative of the denominator. So that's 1. And what is the limit x tends to 0 of cos x? Well, it's just cos 0, which is 1, right? And I think this is, incredibly simple and beautiful. And in this video, we're not going to understand how it works. That's a little more involved. But the beauty is that it works, and differentiating a function, unlike integrating it, is very easy and trivial in most cases. So this is a really powerful and really easy to apply rule. Let's look at another example just so that we at least clearly understand how to apply the rule, right? So the second example we want to look at is the limit x tends to infinity of log x over x. So let me just move all of this to the left so that we have some space for the second example, which I can do here actually. So what is the limit x tends to infinity of log x over x? So again, the first thing we want to do is just plug in infinity into the limit, into the function. So log infinity over infinity is of the form infinity over infinity. So again, L'Hopital's rule says, okay, if it's of the form infinity over infinity, what you do is apply the limit again, but this time you take the derivative of the numerator, which is 1 over x, and divide that by the derivative of the denominator, which is 1. And what is the limit as x tends to infinity of 1 over x? Well, that's 0, right? And this is kind of intuitive because if you look at the graph of log x, so let's quickly, as a side note, just try to, I always try to think of things graphically because I think that's one of the most powerful tools in our toolkit when it comes to mathematics. So log x looks something like this, correct? And x looks something like this, okay? So as x gets larger and larger, x is just going to grow much more faster than log x. Log x is going to saturate because the derivative of log x is 1 over x, right? So that means the graph is going to get flatter and flatter and flatter as x gets larger, while x is just going to continue to grow linearly. So as x gets very large, log x over x is going to tend to 0, right? So this makes sense. So these are very simple examples, and that's not the purpose of this video nor this channel. So today, now that we have reviewed what L'Hopital's rule is, let's look at some more interesting examples of L'Hopital's rule. Okay, so the first example is, what is the limit as x tends to infinity of e power x plus e power minus x divided by e power x minus e power minus x. And let me just pull this down here so that we have an entire row to write on. Okay, so what is this of the form? Well, e power infinity is infinity, e power minus infinity is 0. So this is of the form infinity over infinity, which is perfect for L'Hopital's rule. So let's go ahead and apply the rule one more time. So limit x tends to infinity, we differentiate the numerator, so that will be e power x minus e power minus x, and we differentiate the denominator, right? So that will be e power x plus e power minus x. Okay, and now let's plug in the limit. So this is, what is this going to be? E power infinity is infinity once again, e power minus infinity is 0. So this thing is again of the form infinity over infinity. So that means L'Hopital's rule is still valid. So let's try this one more time. So limit x tends to infinity, and we differentiate the numerator, so that's going to be e power x plus e power minus x, and we differentiate the denominator, so that's e power x minus e power minus x. And for those of you who are very alert, you probably realized that we ended up with the same thing that we started off with, right? So in one step we actually flipped the numerator and denominator, and in the second step we actually got back to where we started, which means this is a never-ending loop, right? If we do it one more time, we're going to get to this, and if we do this 2 more times, we're going to get back the same thing. So how do we fix this? So I encourage you to pause the video here and think about this, and think about whether this function actually converges or we're making a mistake in applying L'Hopital's rule. So hope you're done thinking about the problem. It turns out that L'Hopital's rule, even though it's really powerful, sometimes it takes a little bit of algebraic manipulation to bring it into the form such that it can converge quickly. So what do I mean by that? So let's take an alternative approach for the same problem. So let's rewrite this problem as, so this is the limit x tends to infinity, e power x plus e power minus x is 1 over e power x, and the denominator would be e power x minus 1 over e power x, right? So this is going to be the limit as x tends to infinity of e power 2x plus 1 divided by e power 2x minus 1. So I didn't do anything at all. All I did was in essence just multiply the numerator and denominator by e power x, or you can convert it into this fractional form, and then I think you get the idea, right? So now let's first of all evaluate whether this is in the form that L'Hopital's rule prescribes. So when x tends to infinity, the numerator is infinity and the denominator is infinity, which means this is of the form infinity over infinity. So L'Hopital's rule can indeed be applied. So what do we get when we apply it? Well, e power 2x, the derivative of the numerator would be 2 e power 2x. And the derivative of the denominator is also 2 e power 2x, which means this is going to equal 1. And I think this makes sense because as x gets larger and larger, e power minus x is going to get really small, which means e power x plus e power minus x is basically the same as e power x minus e power minus x. So intuitively 1 seems to be a right answer for this. But that's not the point. The point is sometimes L'Hopital's rule can get stuck in an infinite loop, and in some cases it takes a simple but powerful algebraic sleight of hand to convert it into a form where it can just converge quickly in one step, right? So this is the bottom line of this video, that L'Hopital's rule is really powerful. Sin x over x can be easily evaluated to 1, log x over x is easily evaluated to 0, but sometimes there exist some functions that you may get stuck in an infinite loop if you just apply it blindly. So in those cases, I hope this video gives you an idea about some algebraic manipulations that you can do to quickly convert it into a form that converges. So having taken a look at one example, let's look at another one. So let's look at the example of limit x tends to infinity of x raised to the power of half plus x raised to the power of minus half divided by x raised to the power of half minus x raised to the power of minus half. So this is of the form, this tends to infinity, this tends to 0, this tends to infinity, this tends to 0. This is of the form infinity over infinity, which is good for L'Hopital's rule, right? So let's take the derivative. The first derivative would be 1 by 2 x to the power of minus 1 by 2 minus 1 by 2 x to the power of minus 3 by 2 divided by 1 by 2 x power minus 1 by 2 plus 1 by 2 x to the minus 3 by 2, right? So the 1 by 2's cancel, the numerator and denominator. And now the important thing to observe is originally we started off with an infinity over infinity form, but now when we plug in x equals infinity, we get a 0 over 0. But the good thing is L'Hopital's rule also works for 0 over 0, right? So let's apply it one more time. So this is going to be the limit as x tends to infinity of minus 1 by 2 x to the minus 3 by 2 plus 3 by 2 x to the minus 5 by 2. And that's going to be divided by minus 1 by 2 x to the minus 3 by 2 minus 3 by 2 x to the minus 5 by 2. And I hope you see the pattern, right? We are again of the form 0 by 0, but this thing is just going to keep going on. So the 3 by 2 is going to become 5 by 2, and the 5 by 2 is going to become 7 by 2. We are always going to end up with the form 0 by 0. The first step was infinity over infinity, then a 0 by 0 and a 0 by 0 and so on. So this is again another infinite loop that we got ourselves into. So how do we solve this? So I encourage you to pause the video one more time, and actually the solution is not too different from what we did earlier. So hope you can quickly find the solution, and hope you're done trying the problem by yourself. So it turns out that all you have to do, again, let's look at an alternative approach, is just, let's just write it in a format that's probably less intimidating, because once you see all of these powers and everything, it might look complicated, but essentially it's the square root of x plus 1 over the square root of x divided by the square root of x minus 1 over the square root of x. And then this can be simplified to, if you multiply the numerator and denominator by the square root of x, this is just going to be x plus 1 divided by x minus 1. Isn't that fascinating that this thing actually just simplifies to this? And now we're again with the form infinity over infinity, and I think many of you may already have guessed the answer, but when you differentiate the numerator and denominator, you get 1 over 1, which is just 1. And I think this answer makes sense to me again, because square root of x is going to get larger and larger. 1 over the square root of x is going to get to tend to 0. So essentially the square root of x plus 1 over the square root of x is the same as the square root of x minus 1 over the square root of x, as x gets larger and larger. So this thing is going to tend to 1. So to summarize, L'Hopital's rule, let's see, where did we start? L'Hopital's rule is really powerful, right? It can help you solve limits that are of this indeterminate form of 0 by 0 or infinity over infinity very easily. Again, because differentiating, unlike integration, is trivial in most cases. But there are some examples, two of which we saw today, where you may get stuck in an infinite loop unless you modify the function to a form where it can quickly converge to a determinate form. So next time when you are stuck in this infinite loop when you're applying L'Hopital's rule, I hope you remember this video and just take a step back and see how you can simplify the function to a form where it converges in hopefully one or a few iterations. So with that, I hope you found this video useful, and I'll see you in the next video. Bye.